For 500 years, science has stood on one fundamental principle. Earth is not special. We're not at the center. Not unique. Just average. A random speck in a vast, uniform cosmos. Copernicus taught us this. We orbit the sun, not the other way around. Then we learned the sun is one star among billions. The Milky Way, one galaxy among trillions. Everywhere you look in the universe, basically the same. Same laws, same structure, same density of matter. What if that's wrong? What if Earth sits near the center of a billion light-year void? A cosmic bubble where matter is 20% less dense than it should be. And what if that explains the biggest crisis in cosmology? The Hubble Tension. Dark energy measurements that don't match. The fate of the universe uncertain. Right now, in October 2025, cosmologists are fighting over this. Because if we're cosmically special, everything needs to be reconsidered. 1543. Nicholas Copernicus publishes De Revolutionibus Orbium Celestium. The radical claim: Earth orbits the sun. We are not at the center of creation. For over 1,000 years, humans had believed Earth was special, the cosmic center, God's stage for humanity's drama. Copernicus said, "No, we're just another planet." Then the demotion continued. 1600s. The sun is just another star, not special. 1920s. The Milky Way is just another galaxy, not special. 1990s. Our solar system orbits in the Milky Way's suburbs, definitely not special. This pattern became a principle, the cosmological principle. The universe on large scales is homogeneous and isotropic. Homogeneous, the same density of matter everywhere. Isotropic, looks the same in all directions. No special locations, no cosmic centers. Just uniform expansion in all directions. This principle underpins all of modern cosmology. The Lambda CDM model, our standard theory of how the universe works. The math is simpler if the universe is the same everywhere. Symmetry makes equations tractable. But what if the principle is wrong? What if our location is special? The crisis started innocently enough. Two ways to measure how fast the universe is expanding. The Hubble constant, h0. Method 1. Study the cosmic microwave background, the afterglow of the Big Bang. Use it to calculate what h0 should be today. Result? 67 to 68 kilometers per second per megaparsec. Method 2. Measure supernovae and Cepheid variable stars. Direct observations of the local universe's expansion rate. Result? 72 to 75 kilometers per second per megaparsec. That's a 9% difference. And the error bars don't overlap at all. Both methods are precise. Both teams checked and rechecked. Nobel Prize-winning work. They can't both be right. 2019. Tension noticed. Probably measurement error. 2021. Tension persists. This is a problem. 2023. Tension worsens. This is a crisis. October 2025. Still no resolution. But a provocative idea is gaining ground. What if the local measurements are higher? Because we're inside a void. A void so large, it breaks the cosmological principle. 2013. 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, publish a paper. They'd been counting galaxies, mapping the local universe in infrared light, and they noticed something strange. Within about 1 billion light-years of Earth, there are fewer galaxies than there should be. Not slightly fewer, about 20% less dense than the cosmic average. The KBC Void, named after its discoverers, also called, somewhat unflatteringly, the local hole. Size, approximately 2 billion light-years across. To put that in perspective, Earth to Sun, 8 light minutes. Solar System edge, 1 light-year. Milky Way diameter, 100,000 light-years. Local supercluster, 500 million light-years. KBC Void, 2 billion light-years. It's enormous, and we're near its center. Not quite at the center, but within a few 100 million light-years of it, which violates everything Copernicus taught us. Voids are natural. The universe has structure. After the Big Bang, tiny quantum fluctuations created slight variations in matter density. Over billions of years, gravity amplified these variations. Dense regions got denser. Matter flowed into them, formed galaxies, galaxy clusters, superclusters. This creates the cosmic web. Filaments of galaxies connected by dark matter strands. And between the filaments, voids. Most voids are 100 to 300 million light-years across. Expected, normal, part of cosmic structure formation. But the KBC void is different. It's too large, too underdense, too well-defined. In 2020, researchers ran simulations. They modeled 1 million random locations in a lambda CDM universe, counted how often voids this large appear. Result? A void this large and underdense should appear less than 1% of the time. We shouldn't be in one, but we are. And that's only the beginning of the problem. The KBC void isn't just in one dataset. It shows up everywhere. Near-infrared galaxy surveys, 20% underdense out to 1 billion light-years. Clear signal. Radio surveys, same underdensity. Confirmed. X-ray observations of galaxy clusters. Fewer clusters than expected locally. Consistent with void. And here's the smoking gun. The velocity field. Galaxies inside the void are moving peculiarly. Not just expanding with the Hubble flow. They're being pulled outward, toward the denser regions beyond the void. This is gravity at work. Matter attracts matter. The dense regions outside the void pull on galaxies inside it. Bulk flow measurements. The average velocity of galaxies in large volumes. Match what you'd expect if we're in a void this size. May 2025. A new paper tests this using baryon acoustic oscillations, the standard ruler of cosmology. Result? The void model fits the data 100 million times better than a void-free model. 100 million to 1 odds. The void is real, and it's affecting our measurements. So how does being in a void explain the Hubble tension? It's actually elegant. Imagine you're inside a void. Matter is flowing outward, pulled by gravity toward denser regions outside. From your perspective, galaxies appear to be moving away faster than they would in a uniform universe. Their light is redshifted, not just from cosmic expansion, but also from this peculiar outward motion. When you measure the Hubble constant locally using supernovae within the void, you get a higher value. Not because the universe is expanding faster everywhere, because your local patch is special. But when you measure H0 using the cosmic microwave background, light from when the universe was 380,000 years old, long before our void formed, you get the true universal average. The discrepancy isn't a crisis, it's geography. We're measuring two different things: the universal expansion rate, CMB method, our local expansion rate, supernova method. They're both right, they're just measuring different regions. But here's the problem. Most cosmologists don't buy it. The void explanation faces fierce resistance. Critics argue. Argument 1. The void is too large for lambda CDM. In standard cosmology simulations, voids this big shouldn't exist, or if they do, they should be extremely rare. The fact that we're in one is statistically suspicious. Some say, this is just anthropic selection. We observe from where we are. Of course, our location affects measurements. That doesn't mean the cosmological principle is wrong. Argument 2. The void would need to be perfectly tuned. For the void to explain the Hubble tension perfectly, it needs to be exactly the right size, approximately 2 billion light-years. Exactly the right underdensity, approximately 20%. With us positioned just right, near center but not quite. Critics say this is suspiciously fine-tuned, like arranging the universe just to solve our measurement problem. Argument 3. There are other explanations. Maybe dark energy evolved differently in the early universe. Maybe our instruments have systematic errors. Maybe we need new physics. And besides, Occam's razor says prefer simpler explanations. A local void requiring specific size and position. Complex. Systematic errors in measurements. Simpler. But the void proponents have data on their side. To model an inhomogeneous universe, one that's not the same everywhere, you need different math, the LTB metric. Named after Georges Lemaitre, Richard Tolman, and Hermann Bondi. Standard cosmology assumes a homogeneous universe, same density everywhere, simplifies the equations enormously. But LTB allows for variations, different densities in different regions, more realistic, also more complicated. Using the LTB metric, researchers modeled the KBC void's formation and evolution. 2020. Hasselbauer, Banach, and Krupa published the most detailed model. They simulated how the void formed from initial conditions, how galaxies flowed within it over billions of years, what the Hubble constant would look like from our position. Predictions. Local H0, 72 to 73 kilometers per second per megaparsec. Matches supernova measurements. CMB H0, 67 to 68 kilometers per second per megaparsec. Matches Planck satellite. Bulk flow velocities. Check. Match observations. Galaxy number density. Check. Match infrared surveys. The model works. It fits everything. But it requires something most physicists resist admitting. May 2025. The National Astronomy Meeting in the UK. Indranil Banach, a cosmologist at the University of Portsmouth, presents new results. His team compiled 20 years of baryon acoustic oscillation data, the standard ruler measurements cosmologists use to track cosmic expansion. BAO, baryon acoustic oscillations, are ripples in matter distribution from the early universe. Sound waves frozen in place when the universe cooled. These ripples provide a ruler, a standard length, about 500 million light years. By measuring this ruler at different distances, different times in cosmic history, you can track how the universe expanded. Banach's team compared two models: void-free model, standard lambda CDM, homogeneous universe; void model, KBC Void, Inhomogeneous. They fed 20 years of BAO data through both models. Result? Chi-squared for void-free model, 75.7. Chi-squared for void model, 47.3 to 51.2. Lower chi-squared equals better fit. The void model is 100 million times more likely than the void-free model. The void-free model had 3.3 sigma tension with the data. The void models, 1.1 sigma to 1.4 sigma. Basically consistent. This is the strongest evidence yet. But it gets better. Here's a prediction the void model makes. If the Hubble tension is caused by us being in a void, the discrepancy should decrease with distance. Close to us, inside the void, high measured H0, about 73 kilometers per second per megaparsec. Far from us, outside the void, lower H0, closer to the CMB value, about 68 kilometers per second per megaparsec. There should be a transition, a decay in the measured value as you look further out. 2023 to 2025, multiple studies measured H0Z, the Hubble constant, as a function of redshift. Used supernovae, baryon acoustic oscillations, cosmic chronometers. Result: the measured H0 is highest at low redshift, nearby, decreases with distance, exactly as the void model predicts. The shape of the decay curve matches the void model prediction closely. This wasn't predicted by any other explanation for the Hubble tension. It's unique to the local void hypothesis. And then March 2025 added another piece to the puzzle. March 19, 2025. The Dark Energy Spectroscopic Instrument Collaboration announces new results. DESI has created the largest 3D map of the universe ever made. 14 million galaxies and quasars, spanning 11 billion years of cosmic history. Their goal? Study dark energy, the mysterious force accelerating cosmic expansion. Their finding? Hints that dark energy might be evolving. Not a constant, changing over time. Statistical significance: 2.8 to 4.2 sigma, depending on data combination. Not discovery level, 5 sigma yet, but intriguing. Now DESI's result seems unrelated to the void. They didn't mention it. But here's the connection. If we're in a void, and that void affects our measurements of cosmic expansion, it also affects how we infer dark energy's properties. Dark energy's equation of state, how its density changes over time, is calculated from expansion measurements. If those measurements are contaminated by void effects, then dark energy might appear to evolve, even if it's actually constant. The void makes local expansion look faster. That mimics evolving dark energy. Or here's another possibility. Maybe dark energy is constant, and the evolution DESI sees is actually the signature of us, moving through different density regions as we look back in time. The void explanation keeps getting more compelling, but it requires accepting something uncomfortable. If the KBC void is real and it explains the Hubble tension, here's what it means. Implication 1. The cosmological principle is violated on billion light-year scales. The universe is not the same everywhere, at least not on scales smaller than a few billion light-years. Our local patch, 2 billion light-years across, is significantly underdense, and we happen to live in it. Implication 2. Dark energy might not exist, or it works differently than we thought. We invoked dark energy to explain why the universe's expansion is accelerating. But if local measurements are inflated by the void, maybe the universe isn't accelerating as much as we think. Or maybe dark energy is real, but our measurements of its properties are contaminated. Either way, major revision needed. Implication 3. The universe might be older than we think. The universe's age depends on the Hubble constant. Lower h0 equals older universe. If the true universal h0 is 67 kilometers per second per megaparsec, the CMB value, not 73, the local value, the universe is about 13.8 billion years old. That's 600 million years older than if we use the local measurement. This matters because we found some stars that appear almost as old as the universe. If the universe is younger, using h0 equals 73, those stars are impossibly old. If the universe is older, h0 equals 67, void explanation, the ages work out. Implication 4. We are cosmically special after all. For 500 years, science has taught us we're not special. But if we're in a massive void near its center, we are in an atypical location. Not theologically special, not divinely chosen, but statistically atypical. And that's philosophically uncomfortable. There's a reason scientists resist the void explanation so strongly. It feels like going backward. The Copernican revolution was about humility, accepting we're not the center, not special. It shaped all of modern science. If we're in a special location, it invites anthropic reasoning. Of course we're in a void. If we weren't, we'd measure different values, and cosmology would look different. And maybe intelligent life wouldn't have evolved to ask these questions. This leads to fine-tuning arguments. The universe seems designed for us to exist in this particular void. Scientists hate fine-tuning arguments. They stop inquiry. They're unfalsifiable. But here's the thing. The universe doesn't care about our philosophical preferences. If the data says we're in a void, we're in a void. Science is about following evidence, not protecting principles. We've been here before. Continental drift, resisted for decades because it seemed implausible. Eventually, evidence won. The Big Bang, rejected by many because it implied a beginning. Evidence won. The void hypothesis has galaxy count data, 2013. Multi-Wavelength Confirmation, 2015 to 2020. Velocity field matches, 2020 to 2024. BAO data fits, 2025. Redshift-dependent H0 decay, 2023 to 2025. At some point, evidence overcomes philosophical discomfort. But not everyone is convinced yet. To be fair, the void isn't the only proposed solution to the Hubble tension. Some propose early dark energy, a component in the early universe that changes the expansion history. This would alter the CMB-derived H0 prediction. Problem: early dark energy creates other tensions. It's hard to make it fit all the data simultaneously. Others propose modified gravity. Maybe Einstein's general relativity needs correction on cosmic scales. Problem: GR has passed every test so far. Solar system, binary pulsars, gravitational waves. Hard to modify it without breaking something else. The most conservative explanation: systematic errors in one or both measurement methods. Maybe supernovae aren't perfect standard candles. Maybe CMB analysis has hidden assumptions. Problem: the Hubble tension shows up across multiple independent methods. Supernovae, Cepheids, tip of the red giant branch, gravitational lensing time delays. All show higher H0 locally. All would need the same systematic error in the same direction. Coincidence? Or are they all measuring the same real effect? Being in a void. The next few years will decide. So how do we settle this? More data. The Vera Rubin Observatory, currently commissioning in Chile, will map the southern sky starting in 2025. It'll provide the most detailed map ever of large-scale structure, including the KBC Void. The Euclid Space Telescope, launched in 2023, is mapping billions of galaxies. Its data will test whether the void's structure matches predictions. DESI continues observing. By 2026, it'll have mapped 50 million galaxies. More data on dark energy evolution. More constraints on the void model. The Nancy Grace Roman Space Telescope, launching in 2027, will study dark energy with unprecedented precision. The definitive test: do observations at different distances and in different directions show the systematic patterns the void predicts? If yes, the void is real. If no, back to the drawing board. Timeline: 2 to 5 years for strong evidence. Maybe 10 years for consensus. That's fast in cosmology, and the stakes couldn't be higher. October 2025. We live in a cosmic void, probably. The KBC Void. 2 billion light-years across, 20% less dense than the cosmic average. With us near the center. It shows up in galaxy counts, radio surveys, X-ray observations, velocity fields, baryon acoustic oscillations, Redshift-dependent Hubble constant. The May 2025 analysis found it's 100 million times more likely than a void-free model. But most cosmologists aren't ready to abandon the cosmological principle yet. Too radical, too uncomfortable. Too much like going backward to a special Earth. And yet, the data keeps accumulating. Every new survey, every new test, the void explanation fits better. We are either in a statistically unlikely but real cosmic underdensity, experiencing an elaborate coincidence of systematic errors, missing something fundamental about cosmology. One of these is true. We just don't know which yet. The irony is profound. Copernicus taught us, you're not special. Earth isn't the center. 500 years of science confirm this, again and again. We're just ordinary matter in an ordinary galaxy in an ordinary part of the universe. And now the data might be saying, actually, your location is special. Not divinely, not by design, but statistically. You happen to live in a cosmic void, A billion light-year bubble of underdense space. And here's the kicker. Copernicus was right that Earth doesn't orbit at the center of the solar system. But we might orbit near the center of a local cosmic structure anyway. We're not special on solar system scales or galactic scales. But we might be atypical on billion light-year scales. And typical again on scales larger than that. The universe is messier than our principles want it to be. The next decade will test this. Rubin Observatory, Roman Telescope, DESI's final data. We'll know if we're in a void, and if that void explains dark energy, and the Hubble tension, and the fate of the universe. We live in a cosmic void. Maybe. This is Cosmic Canvas, where we map the universe, even when it challenges everything we thought we knew. Until next time, stay humble, stay curious, and remember, you might be more cosmically special than you think.